Hi, I'm Ben Hirschberg. I'm going to talk to you today about how many CPU cycles you need to invest in your cloud security. So really short about me. I'm an ex-white hat hacker with a long history of security and testing and development. And today I'm an entrepreneur in the cloud native field, and the cloud native security field, to be more precise. And I have a few hobbies. One of them is teaching, and I love to present such interesting things that like what I'm going to present to you today. So what we are going to do today is we are going to talk about TLS and in cloud native and how much we need to invest in TLS. We are going to run some benchmarking tests. We'll try to understand how much we really need to invest in order to move from non-protected connections to TLS. We'll try to learn together how these numbers are built up. And at the end, hopefully, I will be able to tell you a few improvements you can make to improve the time your TLS performance. Okay, so why are we talking about TLS and cloud security at all? So in general, obviously, all of us know that in the recent, I can say 10, 15 years. Cyber attacks has dipped to a higher level, and we see that these not just many money goes into the protection, but also a lot of money going into the attacks, and there's a big interest in attacking systems, and therefore when we are moving to cloud, and somehow we are even a little bit losing our connection with our physical systems, we even need to invest a little bit more into our security than before. And TLS is a cornerstone of cloud security. Okay, and we have to do all of this while keeping our expenses at a reasonable level. Okay. Wait a second, please just moved. Okay, so what is TLS? I don't want to speak too much about it because this is not a security lecture. I assume that you have some knowledge of TLS, but just for the sake of the discussion, so TLS is Security Communication Protocol. Today, it contains nearly all more interesting security features which we need in a secure connection protocol. We have confidentiality, encryption, integrity, which is message authentication, authenticity, where we can validate the communicating parties in our connection, and all of these are given. TLS gives these features, and TLS does it by using nearly all of the new and modern crypto algorithms are around in the world, and TLS continuously updates its list of crypto algorithms depending on whether a new algorithm comes up or something becomes broken. And going forward, what we need to understand is what are the parts which are building up TLS. In order to understand how much we need to invest, we have to break the protocol into its parts and see which part does what and how much time it takes. So the handshake protocol is the first part of any TLS connection establishment. It has two main goals. Okay, one goal is to authenticate the communication parties in the connection, whether it is a one-part TLS, which we call single-sided TLS, or a mutual TLS, where we are both parties are authenticating the other. What it does is authenticate that we are really talking to one to whom we wanted to talk, and the second important part is that it creates what we call a session key. So handshake protocol is results in two things, main things. One is the authentication of the peer. The second is the creation of a session key. Now, the session key is a symmetric key. Okay, the handshake protocol mostly is based on asymmetric cryptography. Okay, I don't want to go into that deeper right now, but in order to authenticate the peer without knowing its secret is based on by asymmetric cryptography. But asymmetric cryptography is a computationally high demanding field. And on contrary, symmetric cryptography which is used by the application protocol is a less computationally intensive field, and therefore one of the main goals of the handshake protocol is to create a symmetric key between the two parties who haven't met before. And the application protocol, which is the main part from the application point of view of the TLS protocol, is actually the part where TLS takes the application data, let it be HTML or gRPC or any other kind of TCP based protocol, and wraps it in a secure enclosing, encrypts the data, and creates a message authentication code, which enables the other side to validate that it really got the original message it wanted to get. And this is done using symmetric cryptography, using the session key created in the handshake protocol. The third part of the TLS protocol is alert protocol, which is not really interesting for the sake of our discussion today. But for the completeness, I'm telling you that it exists alert protocol. It doesn't have to really do something with cryptography. It's only a way to alert the other side that something really went wrong with the signatures or other parts of the handshake or the application protocol, and alert the other side that something is wrong and we are going to disconnect. So, as I told you, we are going to mostly talk about CPU today, and I wanted to give you an outline of computational intensity of the handshake protocol and application protocol as the opening of our discussion. If we look at handshake protocol and how much CPU it needs, as I told you before, it is based on asymmetric cryptography, and asymmetric cryptography takes time and it takes CPU. So it's for a short time, but it loads the CPU really pretty heavily, relatively, and this has to be taken into account. On the other hand, the handshake protocol itself doesn't use really much RAM. I mean, it uses a few kilobytes, but it's not something that really worries us altogether. And also, from a network perspective, the handshake protocol is taking a few kilobytes at the beginning of every session opening, which, if we compare against pure TCP connections, which was a few tens of bytes, there is some considerable addition at connection opening and overhead to TLS. On the other hand, if we look at the application protocol, as I told you before, the asymmetric cryptography of the application protocol is relatively less CPU intensive, but obviously this has to take into account the number of bytes which is being transferred over the application protocol. So if we take the handshake protocol as a given, every connection open this is a constant number. Application protocol CPU usage depends on the number of bytes which is meant to be transferred over the connection. Therefore, this is really a relative impression I can tell you at this stage, but it's a little less than handshake CPU intensive than the handshake protocol itself. The same goes from RAM. From the RAM perspective, the application protocol is not really using more RAM than without TLS, and also its overhead over the wire is pretty small. It's like 20 to 30 bytes per TLS frame, which is like something we can easily manage. I also wanted to, before going into the benchmarking, to talk about the types of TLS and the use cases. So we have the north-south traffic use case, which is mostly the endpoint talking to our backend side, to usually today talking in the cloud into application load balancers of some type of, or an ingress controller. And there is TLS termination usually at this stage. So usually the incoming TLS against the public internet is one-sided, because usually the clients, the endpoints, want to verify before they send some kind of authentication token or credential. They want to verify that they are talking to the right server, and there is no real point on validating the endpoint identity at this stage. So it's one-sided TLS. And usually we terminate it somewhere at the beginning, because usually application load balancers, ingress controllers usually want to look into the TLS traffic, into the traffic, the application level of the traffic, in order to do intelligent stuff. On the other side, we have the east-west traffic, okay, and up until the cloud transition, okay, we usually closed the east-west traffic within a firewall into a perimeter. But today, going into the cloud-native world, okay, these old perimeter setups and concepts are less and less elastic and expandable, and therefore we see that more and more that the east-west traffic needs to be protected, because there is no clear perimeter around it. There are three examples which I brought in how to do east-west setup. One is which I called homebrew, taking existing applications and adding TLS to them, which is pretty complex from the operational point of view, because we start to have to manage every service with its own private keys and certificates, which is a big fuss. And therefore, we have our service mesh solutions like Istio, which are using sidecars. And within CyberArmor, we are using, for the same purpose, we are using what we call the inline-based setup, where we are not using a sidecar proxy, but we are adding an extra component to the process in order to upgrade existing connections to TLS. And both in Istio and in our case, we are managing the certificates and private keys instead of the application developers or the operators. Okay, well, in this east-west case, we see more dominance of mutual TLS use case, where both services which are talking to each other, authenticating themselves to each other. Okay, and we have to know here that both mutual TLS are adding extra CPU usage because of the secondary authentication, and the sidecar proxy is adding extra RAM and CPU usage to the system. So my simple setup started from adding using Apache JMeter against a simple Nginx static web server. I've used different file sizes in the static web servers: 1 byte, 1 kilobyte, 1 megabyte, and 100 megabyte, and gave it 4 CPUs per microservice. And I started to run my first benchmark. And I got to really dramatic initial results, because what I saw that if we are moving from clear to TLS, our performance is dropping very rapidly. So if I'm looking at the right side, requests per second, if I'm requesting a 1 byte file from the web server, going from 4,000 requests per second to merely 300. If I'm going to the other end of the scale and going to files with 100 megabyte content, then I can see that although the ratio is not 1 to 10, but still 1 to 4, and it's a pretty high ratio. So at this time, I was, you know, not that I was puzzled, but I saw that this is not really a good way to calculate things and get to somewhere from here. And I went through to start to do some calculations, doing bottom-up calculations to understand how much every part of the TLS takes and how much addition it gives to my existing application. Using both network capture and after performance monitoring tools like perf, I've calculated rough numbers of TLS handshake. And I got to numbers that the TLS handshake constantly in every connection takes like around 2 milliseconds on the client side and around 1 millisecond at the CPU side, the server side. This is for server certificate validation, but if we are doing mutual certificate validation by two sides, then obviously the client CPU time goes up, also server CPU time goes up a little bit. And I got I got to measurements of 2.5 milliseconds per side, calculating the TLS handshake. Now this is given one of the today's in 2020 the most common key exchange and handshake algorithms like elliptic curve Diffie-Hellman with RSA signatures and 2 kilobit keys. I did the same, tried to make up same rough numbers for the application protocol, when in the application protocol we do encrypt every byte and hash them also to create a message authentication code. I got to the numbers of 250 megabytes per second for an AES 256 bandwidth, and for message authentication like 300 megabyte per second for SHA-3 256. Okay, and these are rough numbers. And we'll try to improve it at the end, but this is some kind of good start. And from this, I could see that we can get to something like 143 megabytes per second we need to calculate with as a bandwidth for a CPU. So. And this is, sorry, this is going to be the hardest part of our discussion. I hope it is not that hard, but I've created a small and simple formula for calculating this TLS overhead. Okay, I took into account the number of transactions I want to make, which is N. The H is the client or the server side the CPU time we need for the handshake. S is the encryption bandwidth, and T is the bytes in one transaction. And using this formula, I want to calculate the overheads of TLS, of how much time I need for n transactions to calculate TLS. Or on the other hand, I can calculate also and invert this formula, and I calculated how many transactions I can make in a given time. So using this formula, I could represent what we need to know and what we need to calculate. On the one hand, you can see here in the first line that on the I start by beginning to calculate the number of time we need for the handshake, both on the client and server side, and on the left side I can I've added how much time I need for encrypting and validating the application protocol messages for TLS, and from this I could explain how many transactions I can do within a simple second by inverting this formula. So I took return to my original test setup, but this time I've used only a single core. I've created a test application, which I call him test application 1, where in every TLS, I do a TLS handshake per every TCP connection. I don't use keep alives. What I do is I've using the same crypto parameters as described before, and I'm requesting 1 kilobyte of application data per transaction. And I got to the part where I could calculate the results using my formula, and I got to 331.32 if I round up transactions per second. And when I look in running the same test on JMeter, I got to 328 transactions per second, which shows that it's really close. It's 1% difference between the theoretical and the actual numbers. I did the same for my second application, where I've used 100 megabyte application data per transaction. I got in my formula, I got to 0.68 transactions per second. And when I ran it through JMeter, okay, I saw 0.7 transaction per second, which is, again, it is pretty close, and I was, more or less good with my formula here. But if I want to conclude my formula, I know I have a service where I have 5,000 requests, and I have mutual TLS, and the H and C, 2 H's are 2.5 milliseconds, and I have this crypto bandwidth of application data. When I'm using my formula, I'm and calculated how much time I need, CPU time I need to for these transactions. I saw that I got 25 seconds for 5,000 requests, which is, it's, if you for the first link, it's a lot of overhead, and we understand that the main component here is the handshake protocol itself. Now, if we look into the handshake protocol, how we can improve the handshake protocol itself, at the first step, we have to understand what kind of algorithms we are using in the handshake protocol. And as I told you before, we are using apt-get Diffie-Hellman for the key exchange algorithm. There is no real contest here, because we could use RSA, but using RSA for key exchange algorithm has what we call forward secrecy problems. It means that if someone records today the conversation and is not able to decrypt it, an attacker is not able to decrypt it, but if he steals it, my private key later on, like in 5 years, he will be able to decrypt my old traffic. If I'm using what we call forward secrecy algorithms like Diffie-Hellman, it means that even if someone steals my key in a year, it won't be able to decrypt old traffic, and this is obviously very, very preferable today. So therefore, it is we prefer to use apt-get Diffie-Hellman. Also, the key exchange signing algorithm is RSA with key size of 2 kilobits with SHA-256. The same for the certificate validation. These are the smallest. These are actually more or less the default numbers today. And I have to tell you that going from down there using smaller key sizes and older hashes is really going to hurt your security. Therefore, there is not really much space here to improve your handshake. What can improve your handshake is what we call the world of expedited handshakes. I brought here 2 examples. One is client-side session ticket. It is defined in their TLS RFCs. It enables the client to request from the server on opening the TLS session to give him a session ticket. The session tickets contain the session key encrypted only for the server itself, so the client cannot look into it. But that's not the point, because what it enables that if the client closes the connections and decides to reconnect the same server, can take the same ticket and do an expedited handshake protocol with where the server is taking the ticket, decrypts it, and uses it as a session key, which is like 10 times faster than than doing a new key exchange. It obviously requires the client to remember these tickets and associate it to the servers. But on the other hand, after the creation of the full first handshake, you don't really need to add more to your current transactions, and it's very, very fast. The same with the pre-shared keys. The pre-shared keys is a protocol where you can use TLS with symmetric keys pre-shared among the parties. It is very fast. The same. It enables also even the first connection to be done without full key exchange. But it really has a big burden of pre-sharing symmetric keys, and it's a really big. It's not an easy solution. So it's not really good for our cloud native environments. So just to show you that if we assume, I return to my previous calculation with the formula and assume that we have session tickets and our handshake time is going down by an order of magnitude, okay, from 2.5 milliseconds to the 10th time, we can see that also the time we need to complete the full 5,000 handshake, 5,000 connections is 2.1 seconds, which is less than obviously a very good improvement here. So session tickets are really, really good for performance. Talking about the application protocol is on the one hand it can be improved, and it has a big effect, especially on applications which uses big chunk of memories transferred between the two parties. Mostly today, most new CPUs supporting ASNI, which gives you a fantastic throughput, and it's hardware supported in most Intel chips. Make sure that your applications are using it and using ASNI, because it improves your performance very much in the application protocol. If you don't have hardware support, mostly in IoT devices and embedded devices, you can still use Cha-Cha, which is a less secure algorithm than AES, but still a very good one. And it's less time and CPU consuming. For message authentication, we are suggesting to look into authenticated encryption, which are mostly AS-GCD-like protocols, where you don't need to go through 2 times over the same message, and they give a way better output in the application protocol against SHAs and other message authentication protocols. So I suggest you looking into AS-GCD from this part. I think that we've ended the main part of our discussion. I will be happy to answer your questions now in Q&A, and thank you for your attention. Hi, everyone. Now I'm taking here the questions after the presentation. So the first question is about whether to use RSA or ECDSA. The questioner asked says that I heard that ECDSA is less CPU intensive on the server side, but more intensive on the client side. So the scenario where, in a scenario where both of the client and the server is located in our data center, service mutual TLS, is ECDSA really beneficial over over RSA? So it's a really good question. There are actually two things to think about. One is the security. Okay, as I said in the presentation, using ECDSA for a key exchange algorithm, it has a big benefit from the security side. So you have forward secrecy, which means that if someone records today your conversation and cannot decrypt it,
but will be able to take your keys, steal them at a later phase. He will be able to decrypt them if you are using RSA. On the other hand, if you are using Diffie-Hellman-based algorithms like ECDSA, then I think that the better use is the elliptic curve Diffie-Hellman key exchange. On the other hand, RSA has a big performance upside usually on the client side, because when the server in RSAs, there is known tweak that in RSA the public key can be a very small number, and using a very small number means that there has to be less computation to be done, and using RSA can be beneficial on the client side. But again, the question here relates more to service-to-service mutual TLS case, where in the same data center, I think that using RSA and elliptic curves doesn't really have a big effect, because on the other hand, the server will work harder. And if this is a symmetry case, I would say that there won't be here a big performance improvement. Yeah, let's see the next question. So why I'm waiting for the next question, I'm returning to this original question of whether to use RSA or ECDSA. Elliptic curve algorithms usually have a better performance overall. So usually, if we have the same, we are keeping, using this, we are providing the two sides of the conversation. We have to take into account both sides. Then I think that elliptic curves are making a really good case. But if we can say that we are holding one side of the conversation, and we want to take its performance into the context, like if you have an endpoint which is low power consumption device, or any kind of other device which is limited from the computational perspective, RSA has a good tweak. So there is here no black and white answer, but really, it's a nice engineering question, where the application, the specific parameters of the specific application has to be taken into the account. If there are more questions, I will be happy to take here. If no, then I will be moving on to the Slack channel after this presentation, and I will be happy to answer more questions if needed. Yeah. Okay, so we are moving to Slack right now. I will be happy to take questions there. I was glad that you attended my speech. My lecture. I will be happy to talk to you later.